Required object initializers force assignments, but they cannot tell us whether a failure drill is safe. An empty rollback list still satisfies the compiler. So does a fault added before limiting the blast radius. We will start with a clean, direct solution, not a fake bad example, then add rules that make Builder worth its extra code. A complete drill leaves the Builder. An incomplete one does not. Builder constructs a complex object through a sequence of named steps. Its defining characteristics are private intermediate state, a construction vocabulary, and a final operation that returns the product only when it is ready. 5 participants describe the full pattern. The product is the object being assembled. The builder defines the available construction steps. The concrete builder stores intermediate state and implements those steps. The client chooses a builder and asks for a result. A director may capture a reusable construction recipe, but the pattern does not require one. Common use cases include objects with meaningful stages, optional parts, ordered operations, or rules involving several values at once. Builder can also support different configurations or representations through the same construction vocabulary. Avoid builder when a small object has a few independent values. A constructor, required initializer, or named factory is shorter and easier to follow. A fluent method chain is also not the pattern by itself. Returning the builder from each method is only a convenient API choice. Our product is a resilience drill plan. It names a target service, limits the number of affected instances, describes a fault, lists the signal we will watch, and records the gate that tells us to roll back. Drill Plan Builder will be the builder contract. Resilience Drill Plan Builder will be the concrete builder. Drill Recipes will be an optional director containing one known safe sequence. Program.c# is the client. This demo only constructs configuration. It does not execute a real failure drill. That boundary keeps the example honest and keeps our attention on object construction. Start with the smallest value in the model. Fault injection is a positional record with a name and a duration. Those parameters form its primary constructor. Now create Resilience Drill Plan, the product. Each property is required, so every caller must assign it during construction. Each setter is init-only, so the reference cannot be replaced after initialization. The 3 collections use immutable array, which keeps a caller from changing the accepted plan through a shared mutable list. Move to program.c# and create one plan directly. The plan variable receives a required object initializer. Set the target to inventory API, keep the blast radius at 2 instances, inject 90 seconds of network latency, watch checkout latency at the 95th percentile, and require the error rate to stay below 2% before continuing. Finish with print plan. It prints the values we need to inspect and nothing more. The direct construction is explicit, modern, and readable. For one plan with values already available, this is a good solution. The direct version works. It targets inventory API, limits impact to 2 instances, adds the latency fault, names the signal, and includes the rollback gate. This output is our control result. Builder must preserve it. If the pattern changes the behavior, we have changed the problem instead of improving its construction. The direct code is not wrong. The pressure appears when this safe latency drill becomes a recipe used by several clients. The blast radius must be set before a fault is added. The finished plan needs at least one fault, one observable signal, and one rollback gate. Those are relationships between values, not simple presence checks. The required modifier guarantees that a caller assigns a member. It does not decide whether an empty collection or a zero value makes sense in this domain. We could repeat those checks at every call site. A named static factory could handle one fixed recipe. But we now need a vocabulary for gradual construction and one commit point for the rules. That is the point where Builder starts paying for itself. The Builder contract names the construction steps in domain language. For service, selects the target. Limit blast radius sets the safety boundary. Inject latency adds the fault. Require signal and add rollback gate, add the observation and exit conditions. Build asks for the finished product. Each configuration method returns iDrillPlan Builder. That return type lets the client read the steps as one fluent sequence, but the important design choice is the named construction vocabulary and the delayed product. Resilience Drill Plan Builder is the concrete builder. It owns 3 private lists for faults, signals, and rollback gates. Collection expressions create the empty lists. The service name and blast radius are nullable because construction has not supplied them yet. Type for service. It validates and stores the service name, then returns this builder. Limit blast radius accepts values from 1 through 20. The relational pattern keeps that range check compact. Next comes inject latency. Before accepting a fault, it checks that the blast radius already exists. That rule makes the construction order explicit. It also rejects a duration outside the allowed window before adding a fault injection to private state. Require signal and add rollback gate, validate their text, and append it to their private lists. The helper require text keeps that repeated check in one place. Now type build, the commit point. First, it requires the service and blast radius. Then it checks the whole construction, at least one fault, one signal, and one rollback gate. Only after those rules pass does it create Resilience Drill Plan. The spread elements copy each private list into an immutable array. Construction is allowed to be mutable because that state never escapes. The product returned to the client is complete and immutable. Builder does not make every call sequence valid. It prevents an invalid sequence from producing a product. Drill Recipes plays the director role. Its create safe latency drill method receives the builder contract and records the same sequence we proved in the direct version. The director is optional. We use it because this sequence has a name and may be repeated. If a client needed a one-off custom plan, it could call the builder steps directly. Return to program.c#. Replace the long initializer with a call to create safe latency drill and pass a fresh resilience drill plan builder. The client now states its successful intent in one line. Below that path, add a second fresh builder. Give it a service, blast radius, fault, and signal, but leave out the rollback gate. Catch the expected invalid operation exception so one terminal run can show both results. The product and the print plan body do not change. Run the builder version. The first 5 lines match the control result. Same service, same 2-instance boundary, same fault, same signal, and same rollback gate. The behavior did not change. Responsibility did. Program chooses a recipe, the concrete builder manages construction, and build decides when a product may leave. The success path is only half the proof. The second fresh builder repeated the service, blast radius, fault, and signal steps, deliberately left out the rollback gate, and then called build. The final line begins with blocked and includes the exact missing parts message. The catch exists only so this boundary remains visible beside the successful result. No partial resilience drill plan escaped. The failure happened at the construction boundary before any code could mistake an incomplete plan for a usable one. Builder adds an interface, a stateful implementation, and a lifecycle. That cost is justified when the steps carry meaning, order matters, valid combinations need one final check, or several recipes share the same construction language. Use a constructor when all required values arrive together and the call stays readable. Use required init-only properties when the values are independent and the object initializer explains itself. Use a named factory when 1 or 2 fixed recipes are all you need. The director is optional, and a fluent API is optional. This builder is also intended for one local construction flow. Create a fresh instance for each plan instead of sharing its mutable state. Finally, keep the guarantee precise. Our builder validates the configuration rules we wrote. It does not prove that running a failure drill is operationally safe, and this demo never executes one. We started with a direct initializer because it was the clearest, honest solution. Then repeated construction, ordering, and whole plan validation changed the design pressure. The product stayed focused on accepted data. The builder contract named the steps. The concrete builder held unfinished state and enforced the rules. The optional director captured one reusable recipe. The client received a complete immutable plan or no plan at all. That is the practical decision behind Builder. Use it when the construction process has become part of the problem. When construction is still simple, keep the simpler code.